Okay, everyone, we are now on 13.5, which is on page 931 in your books. And one thing I want to make sure I point out, no longer look at your homework sheet for what to do for your homework, okay? I'm going to post what you need to do. Some things are going to be a little bit different than I initially intended, just given everything going on, okay? All right, so for our first couple definitions, I do have them written out, but again, they are in your books. So a compound event, also called a composite event, I will never personally call it that, but just know that some books do. All that is when you have an event of, you have two or more simple events. So an example of this might be, let's say Jack is chosen first for a group. Okay, or I'll say for a group. And Max is chosen second. That's it. Okay, we have two simple events. Jack is chosen first, so this is our first simple event, and then our second one is he is chosen second. Okay? All right, so for the independent event now, we have X and Z, those are two events, okay? X and Z are independent if the probability that X occurs does not affect the probability of Z occurring. So more times than not, you're going to have independent events. So an example could be something as simple as a cat meows and a dog barks. Those have nothing to do with each other. That's just what happens. Something else could be you get heads when flipping a coin. So you get heads on a coin. You roll a 6. Rolling a dice and flipping a coin have nothing to do with each other. Okay? And for the formula here, probability of two independent events, it's going to be written as P of A, this little lowercase n, and then B. This little lowercase n means the intersection. So if you want to make a note, that n means intersection, but it just means the word and, okay? So we'll put that in quotes here. So the probability of A and B is how you would read that, and that's equal to P of A, the probability of A, times the probability of B. All right, now we also have what are called dependent events, and these are the ones where it gets a little bit tricky. You just have to think a little extra hard about them sometimes. So events X and Z are dependent if the probability that X occurs does affect the probability of Z occurring. So an example of this might be, one of the most common ones is prize drawings with no replacement. So think about a time you entered a raffle here. So without replacement, before I keep going on, if you enter a raffle and there's 4 winners, you'll pick one winner, then you'll pick the next, but you never put the old winner back in the thing. So that's what I mean by without replacement. And our probability of two dependent events, again, it's the probability of A and B, so A intersection B, that's equal to the probability of A times the probability of B given A. So notice how I wrote that right here. I'll put it in a different color. This line, that just means the word given. That's how you write it in math. So the probability of B given that A already occurred. And we'll do some examples below. All right, and our compound event here, all that is the probability that event B occurs given, so we're going to use that line again, given that A has already occurred. Oh, hold on. Sorry, my cat just knocked something over. Anyways, our formula for this, we would write the probability of B given A, and that's equal to the probability of A and B divided by the probability of A. Okay, now we won't be using this one very much. I know it is up here in this formula, but we think about it a little bit differently. So don't necessarily plug this into that formula right away, okay? And you'll see what some of the examples, what I mean by that. All right, in our final definition, we have a probability tree. All that is a tree diagram with our probabilities written on each branch. So for example, we could have our heads and tails for flipping a coin. Let's say I flipped it twice. So I'm going to go ahead and make my tree diagram here. Now the only difference is between my regular tree diagram, I have to write the probabilities on each branch. So I have a 50% chance, so I'm going to write 0.5 for heads. I had a 50% chance there. I'm always actually having a 50% chance, no matter what. Remember, anytime you're flipping a coin, you always have a 50% chance, okay? So again, this section here, that's your first flip. This is your potential second flip, okay? So how we would actually finish off the probability tree, looking here, that represents our heads, right? Here would be getting heads first, then tails, tails first, then heads, and then tails. So our final step for that probability tree is to actually find the probability of exactly getting heads, getting heads, tails, getting tails, then heads, getting tails, tails. So to do that on a tree diagram, because this one it's pretty easy, we can see heads, there's 1 out of 4 chances, so it should be 25%. But sometimes you have really complicated tree diagrams. So what you do is you follow along the branches. So for heads, I'm going to do 0.5 times 0.5, and I get my 0.25, okay? Now again, if you have a more complicated tree diagram, you might have 4 or 5 different branches off of each thing. So that's when this rule comes in handy that I just did. So again, continuing on, we could have gotten a heads first and then a tails. So that would have been 0.5 times 0.5, which equals 0.25. And again, I'm sure you guys can see, if we keep going down, we're going to get 0.25 for each instance here. And just as a quick check to make sure you did this correct, all of your final probabilities here should add up to 1. In our case, they definitely do. Okay, so I might write that as a little note here. We multiply along the branches. So that's for actually finding our probabilities. And then our second bullet point here, we could say we add probabilities down columns. Okay. We won't do a ton with probability trees. They will come into play a lot when you take statistics in high school. So this is just your generic introduction. Okay, now moving on to our examples. So we have to first determine if these events here are independent or dependent. So I think I actually used this up above, but I said a die is rolled and a coin is flipped. Automatically, you should think independent. They have nothing to do with each other. One did not affect the other. Now for the second one, we have a die is rolled and a second die is rolled. So they do both involve dice or die, but again, if you roll one and then roll a second one, that has nothing to do with anything, or each other, I should say. So that event there, again, is independent. Now we have a card is selected from a deck of cards and not put back. That part's your key. Not put back, or that's without replacement. So then a second card is drawn. That definitely is going to affect your probability, because if you didn't put your other card back, your total number of cards to pick that second one is now decreased by 1. So this one's definitely going to be dependent. Like, think if you had 3 cards in your hand and you gave 1 to your sister, and then for your brother, you only have 2 cards left. So you have a 1 out of 2 instead of a 1 out of 3, okay? And our final one, Mondays and Wednesdays lottery numbers. Those have nothing to do with each other. They're completely independent, so we should mark that with an I. All right, we're gonna do the first 2 examples here together, and then I'm gonna suggest you pause the video and do the rest. So looking at this first one, we got a bag, has 3 red marbles and 4 orange. An orange is drawn and not replaced. Again, that's your key phrase right there. Then a red marble is drawn. So we have to say if it's independent or dependent and then find our probability of this given event. So right away, that not replaced means that we're definitely going to have a dependent situation here. So remember, your dependent formula of your P and B, so you can write it out like this, P and B, or I like that shorthand, P and B, just think and has an N in it. Oops, P of A and B, I'm sorry. Remember, for dependent events, that's when we need our probability of A, and we need our probability of B given A. So I like to actually label what each event is. So I'm going to say A is my first event. So that was getting an orange. So orange drawn and not replaced. And then for my B, that was when a red was drawn. All right, so our probability of A, picking an orange. Notice how we had 3 red, 4 orange, so altogether we had 7 total. So picking an orange, I had a 4 out of 7 shot. Now my probability of B given A, now again, you don't need to think back up to this equation in the compound event. That's not going to help you in this instance. Just think about it. If you know you already picked one and you did not replace it, you no longer have 7 to choose from. You now have 6 to choose from. And we're picking a red. We never picked a red in probability or in our event A, so we still have 3 red to choose from. So our probability of B given A is 3 out of 6, or we can simplify that to 1/2. So our final answer of probability of A and B is going to be 4/7 times that 1/2, and we get 4/14, which is 2/7. And again, we can go ahead and put it in a percent. That's roughly 29%, but I'm more than fine if you just have the simplest version of your fraction here. Okay. All right, I'm going to actually say you guys do number 2 on your own. I want to do number 3 with you. So a queen is drawn from a deck of cards, or of 52 cards. You're going to have to actually know what's in a deck of cards. So quick warm up, you have 4 suits. Okay, you got your diamonds, your hearts, your clubs, and your, what am I missing? My spades. Ooh, that was rough. Well, you get the picture. Okay, so you have your 4 suits. You have 13 cards per suit. Okay, 13 cards per suit. You have ace all the way up to king. So ace 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And remember, your hearts and diamonds, those are red. Your clubs and spades are black. And I think that's all I need to say, but I'll mention it if I miss something later on. So anyways, oh, the only other thing I remembered. You have 4 of each card. So what I mean by that, you have 4 aces, you have 4 twos, you have 4 threes, you have 4 kings, you have 1 of each of those suits. You have 4 of each kind of card. So for our next example here, a queen is drawn from a deck of 52 cards. Then a coin is flipped and it lands tails up. So picking a card and flipping a coin have nothing to do with each other, so that's definitely going to be independent. Oops, independent. So our event A, our first occurring event, is our queen is drawn. Okay? Our second one was getting tails on our coin. So remember, your independent, your probability of A and B, all you have to do is multiply your probability of A times your probability of B. So we got to find both of those first. Our probability of A, since we know we're picking a queen and it's not specific about what color or anything like that, we know we have 4 out of our 52 cards. And for tails, that should be pretty simple. We know that we have 1 out of 2 shots of getting tails. So all we have to do, we can choose to simplify this down. I will tell you it goes to 1/13. You don't have to until the very end though. But our final probability is going to be 1/13 times 1/2. which is 1/26. Okay, so I'm going to suggest you pause the video here now and do numbers 2, 4, and then 5. The only thing is I will be back to make sure we can use a probability tree to check our answer. Okay? Okay, hopefully you took time to pause the video. So I have the new stuff here in red. So for number 2, we rolled 2 die and got 5 both times. Again, I mentioned it before, that's going to be independent because they have no effect on each other. So getting a 5 was a 1/6 shot, so we just did 1/6 times 1/6 to get our 1/36. Now down here for number 4, we had without replacement here. So that's your keyword that it's going to be dependent. So our 2 events were picking a black ball first, and then second was picking our non-purple ball. So our probability of getting a black ball, here I'll put in pink, was that 2/16. We just had to add up all of our balls together. We got 2 were black. And then for our second part, the probability of B given A. So the probability that we picked a non-purple ball given that we already picked a black ball. So right away, we know that 16 was going to turn into a 15, okay, since we did not replace it. And then you have to be careful here. Since we already picked a black ball, okay, in our first one, that means up here, I'm going to cross that off, we now only have 1 black. So we have 6 green, 2 pink, 1 black, and 4 red. So if you add all of those up together, we have 13, okay? And then we just multiply them, and we should have gotten 13 1/20. And finally, down here for number 5, we had our green paper and red paper. So we were finding the probability of picking a green twice, and it was with replacement, so it was independent. So we should have gotten 5/11 and 5/11 and multiplied those out and gotten 25 121. So when it said use a probability tree to check your answer, I went ahead and already wrote out our tree. Remember, you just have to make sure that you are in fact writing the probabilities on the branches of the tree, okay? And some books will write the probabilities here and then they would have put the G here. I personally don't care. I think this way is a little bit more clear. So for our green, we got 5/11. Our red was 6 out of 11. So I'm going to go ahead and fill those all in. So our green again was 5. This was 6, 5, and 6. So using that tree diagram, remember when we want to get our column over here, we just have to multiply down the branches. So green would have been 5/11 times 5/11, which is 25/11. Our green-red would have been 30/11 because we're doing 5/11 times 6/11. Oh, I'm sorry, 30 1/21. That should have been 121 up there. Down here we have another 6 and 5, so that's going to be 30 over 121. And our final one is going to be 36 out of 121. Again, we're doing 6/11 times 6/11. And if we add all of those up, we do in fact get 121 over 121. So we know we did it correctly. Okay? So as always, please let me know if you have any questions. And then remember, your homework will be different than what's on that sheet this time.